The goal of this tutorial is to solve the practical problem of a beam in air trying to enter a birefringent material, figuring out what angle the beam is going to refract at, which is a two-step problem, both what direction its wavefront normal will be and what direction the power will propagate at. Let's set up the problem. We've got a material and there's a beam coming into it. I'll start off by trying to solve the normal incidence problem. So we've got a k vector oriented like this. We've got a refractive index n1 out here. Then we've got a material in here. Let's choose a particular example where NO, let's say, is greater than NE. And of course we've got to have some angle that the optic axis actually makes. That's going to be something that we know. I'm going to choose an angle of approximately negative 45 degrees relative to the surface normal. So that's the optic axis. That describes the problem, again assuming that the electric field of this beam is polarized in the plane of the page. We now have a perfectly well-defined problem, and the question is, what direction is this beam going to go? Notice that we've got a Snell's law problem that we can solve first. We know that theta 1 equals 0 degrees. And it's still going to be true that ky equals qy. I'll even write that here to make sure that we can emphasize that. So ky equals qy. That's our first step. That's always true. Always want to satisfy that. And in this case, since the y component of k is 0, y being the up and down component, the q vector must also have no y component. So I'm going to draw a dashed line for the q vector. I'm going to assume this was air, and these numbers are both higher refractive indices than air. So to respect that proportionality to compare with the k vector, I'll make the q vector longer than the k vector. And I've written it dashed because that's not the direction that a thin pencil laser-like beam would go. The power won't propagate that way. So I want to remind you that the q vector tells you the wavefront normal direction and also the wavelength, but it does not tell you the direction that the beam goes. I'll draw that in a solid color. So we already now know one of the two angles that help us solve these problems. We know the angle of the wavefront normal vector q relative to the optic axis. So we can just draw that there. That's the angle gamma. And now if we want to figure out where the Poynting vector goes, we know from previous tutorial that the tangent of alpha, which is the direction that the Poynting vector goes, it's equal to the ratio of NO and NE times the tangent of the first angle, the one we now already know. So if NO is greater than NE, this number will be greater than 1. That means the tangent of alpha is larger than the tangent of gamma. And since these angles are always between 0 and 90 degrees, when the tangent of an angle is bigger than another angle, that means the angle itself is also bigger. Positive angles are defined as being counterclockwise, so that means I have to go a different, larger counterclockwise amount, like say this, for the angle alpha, and that means that the Poynting vector in this problem is pointing at this angle. That I've drawn with a solid line. It's surprising. You've got a beam coming in at normal incidence, and the power does not travel at normal incidence, like we would have, of course, thought it would if the material weren't birefringent. It actually angles away. And if it then encounters, as it does in your homework, another surface, so I'll draw another solid line here to say that this is a material with some finite thickness d, the beam will come out over here, and that's simple geometry to figure out what angle this is. But once it comes out, what angle will it go? When the beam refracts back out again, we had n1 sine theta 1 equals n2 sine theta 2, and n2 sine theta 2 equals n3 sine theta 3. But since n3 equals n1, we are going to have angle 1 equaling angle 3, because n1 sine theta 1 has to equal n3 sine theta 3. So the beam goes in like this, deflects, and comes back out again, even though its wavefront normal is always pointing this way. A little confusing, but that is exactly what the extraordinary beam does. The normal beam, of course, travels through straight like this, and another beam will come out here, laterally displaced from this beam. This problem was easy to solve on direct inspection because theta 1 was 0, so we knew that theta 2, the refraction angle for Q, was also 0. But if we have a case where theta 1 is not equal to 0, in that case, Snell's law would become n1 sine theta 1 equals n2, which is a function of theta 2, times sine of theta 2, where now instead of n2 being a known quantity, a fixed quantity, now it's a function of angle, and we don't yet ahead of time know what angle it's going to refract at. So this becomes a problem that's a little harder to solve than it has been in the past. It is solvable if we just draw out what we're dealing with here. We have a k vector coming in at some angle theta 1. So there's theta 1. The q vector, so this is the wave vector q. And we know the optic axis also. So same problem is up there. And in this case, we still have all the angles that we had before. We know that the angle between the optic axis and the horizontal there, that's going to be some angle psi, which is a given for the problem. We always have to know the angle of the optic axis relative to the interface, or we cannot solve the problem. And we want to figure out what direction the wave vector is pointing. That's what we need to solve for. That's the angle gamma. And the angle that Snell's law needs to satisfy, that's this angle here, theta 2. So there's a relationship between the given angle psi for the problem and then these two different angles, both of which play a role in helping us to solve the problem. So first we solve Snell's law, and to do that we have to remember what the refractive index formula is in general in a birefringent material. If a wave vector is pointing in this direction, it will experience a refractive index, which is a function of gamma. This is something you're solving for on homework, and this is a classic formula that needs to be known by anybody working in this area. NO squared times NE squared divided by two functions of NO and gamma, and a similar expression involving NE and gamma. So we can directly from this blue formula write the refractive index felt by the transmitted plane wave as a function of gamma. Since there's the simple relationship of theta 2 equaling this angle psi minus gamma, we can of course express the refractive index also as a function of theta 2. That's a trivial transformation. So to satisfy n1 sine theta 1 equals n2 sine theta 2, we now can write n2 in this problem is what we're calling here n, and we can write it as a function of angle. Here it's written as gamma, but it could be written as theta 2. So here's how you graphically solve this problem. You set up a plot versus theta 2, and the first thing you do is figure out what n1 and sine theta 1 are. Those are givens of the problem. So you just plot them. You plot a horizontal line. It's independent, of course, of the value of theta 2. That's equal to n1 sine theta 1. But then you plot n2 times sine theta 2, which has a complicated dependence on theta 2 because of the refractive index being angle dependent. And you get some sort of curve that looks like this. I will tell you that it monotonically increases between 0 and 90 degrees, and that's equal to n2 sine theta 2. Now, of course, that does depend on the value of theta 2. And you just look for where the intersection is, and if you plot these two quantities, one a constant, want a variable, you'll find an intersection point, and that intersection point tells you the value of theta 2 at which the refraction will occur. Once you know the value of theta 2, that immediately gives you the angle gamma, and once you know the angle gamma, you immediately can figure out the angle alpha for where the pointing vector will orient.